Section 10.2, the earliest applications of linear algebra. Let's do a bunch of examples, starting with the Ames papyrus, or Rhine papyrus. It's the source of most of our information about ancient Egyptian mathematics. This 5-meter-long papyrus contains 84 short mathematical problems, together with their solutions, and dates from about 1650 BC. Problem 40 in this papyrus is the following. Divide 100 hecats of barley among 5 men in arithmetic progression, so that the sum of the two smallest is 1/7 of the sum of the 3 largest. So by arithmetic progression, we mean that we need some first number, let's say a, and then the next one will be some increment more than that, so a plus d, for example, and then the next one is 2 times that increment, so a plus 2d, then the next one would be a plus 3d, and then a plus 4d. Okay, so that we need all of this together to be 100, because we're dividing amongst the 5 men, so a plus d plus a plus 2d plus a plus 3d plus a plus 4d has to equal 100. And simplifying, we'll get that 5a plus 10d is 100, but we also have this other criteria that the sum of the two smallest is 1/7 of the sum of the 3 largest. So let's write that out too. We'll take 1/7 of the 3 largest, so that's a plus 2d plus a plus 3d plus a plus 4d. And that must equal the sum of the two smallest ones, so it's a plus d. And then, like I said, we'll simplify the top equation, and we'll get 5a plus 10d is 100, and then the second equation simplifies to 11a minus 2d equals 0. So if we plug in a equals 1, then that would tell us that d is 11/2. We're just choosing to plug in an a value because back when, 1650 BC, a common method of solving these types of equations was guessing some sort of value for one of your variables, plugging that value in, seeing what value you get out, and then refining your guess based on how well these two numbers fit into your constraints. So if we started with a equals 1, then plug it into this equation over here, we'd get 5 times 1 plus 10 times 11/2 equals 60. So obviously it doesn't equal 100, so a equals 1 is not the correct answer, but it's a good starting point because we could take a equals 1 times 100/60 now, where you'll refine our choice of a by multiplying it by 100 divided by the 60 that we got. So that's 5/3. And then that gives us a new d value of 55/6. So if we were to plug these in, then we would get 10/6 for a. If we were to keep going, I mean, eventually you keep plugging this in the way that we just did, refining a over and over, and you'll eventually get to 10/6. You get to 65/6 for the second guy, 126 for the third, let's say plus 2d, plus, the next one would be 175/6, and 236 hecats. So notice this is a much different solving technique than we've done, where we could have just solve this using elimination or matrix, etc. But it's kind of interesting the way that they used to do this back then. The Old Babylonian Empire flourished in Mesopotamia between 1900 and 1600 BC. Many clay tablets containing mathematical tables and problems survive from that period, one of which, designated CAMLA 1950, contains the next problem. The statement of the problem is a bit muddled because of the condition of the tablet, but the diagram and solution on the tablet indicate that the problem is as follows. A trapezoid with an area of 320 square units is cut off from a right triangle by a line parallel to one of its sides. The other side has length 50 units and the height of the trapezoid is 20 units. What are the upper and lower widths of the trapezoid? So let's write out an equation for our area. That'll be 20 times x plus y divided by 2 equals 320. Right? Because we have, here's the 20 for the trapezoid. You take the average of the two bases, and the area has to be 320. Okay, but we also know that it fits into this diagram over here where we have some similar triangles. So x divided by y would have to be, or x divided by y would have to be 50, this entire thing, divided by 30. Or you could think of it as x over this entire thing, 50, has to be y over this thing, 30. In any case, we'll set up our proportion. And these two equations together tell us that half x plus y equals 16 and half x minus y equals 4. And then we can solve this as we normally would with elimination or any other method we like and get x equals 20 and y equals 12. The most important treatise in the history of Chinese mathematics is the Zhouchang Xuanshu, or the 9 Chapters of the Mathematical Art. This treatise, which is a collection of 246 problems and their solutions, was assembled in its final form by Liu Wei in AD 263. Its contents, however, go back to at least the beginning of the Han Dynasty in the 2nd century BC. The 8th of its 9 chapters, entitled The Way of Calculating by Arrays, contains 18 word problems that lead to linear systems in 3 to 6 unknowns. The general solution procedure described is almost identical to the Gaussian elimination technique developed in Europe in the 19th century by Carl Friedrich Gauss. The first problem in the 8th chapter is the following. There are 3 classes of corn. I don't know why I said 9. 3 classes of corn, of which 3 bundles of the first class, 2 of the second, and 1 of the third make 39 measures. 2 of the first, 3 of the second, and 1 of the third make 34 measures, and 1 of the first, 2 of the second, and 3 of the third make 26 measures. How many measures of grain are contained in 1 bundle of each class? So let's start out with the first equation, 3x plus 2y plus z equals 39. Then 2x plus 3y plus z equals 34. And then x plus 2y plus 3z equals 26. So this solving method that they used to use back then would take the coefficients and write them out in a cut-off box. So for the bottom equation, we would have 1, 2, 3, and 26. Then for the middle one, 2, 3, 1, 34. And lastly, the top equation gives us 3, 2, 1, 39. And they were in this kind of box like this. Okay, so then after making our box, we worked to reduce the box, very similar to the way that we're used to with Gaussian elimination. So by taking multiples to eliminate, we'll eliminate the 1 and the 2 by subtracting off and so on, so that we can get zeros over there, and we'll just end up with 4, 8, 39, 5, 1, 24, 3, 2, 1, 39. And then, for whatever reason, they don't write the zeros. They just leave the space blank. Okay, so then we keep going. And we'll just get a 0 over here, so that we end up with 36, 99, and then 5, 1, 24, and 3, 2, 1, 39. So you can see that the procedure is very, very similar to what we did before, getting the leading ones and the zeros underneath, and etc. But in this case, they don't really have the ones. So this is it leads you with these equations. The top one is the same: 3x plus 2y plus z equals 39 from the last column. But then the middle one gives you 5y plus z equals 24, and then you get 36z equals 99, and you can solve for z and then plug in, solve for y and x, etc., and you'll get x equals 37 over 4, y equals 17 over 4, and z equals 11 over 4. Perhaps the most famous system of linear equations from antiquity is the one associated with the first part of Archimedes' celebrated Kaul problem. This problem supposedly was posed by Archimedes as a challenge to his colleague Eratosthenes. No solution has come down to us from ancient times, so that it is not known how or even whether either of these two geometers solved it. So it's this kind of elaborate problem, starting with if thou art diligent and wise, O stranger, compute the number of cattle of the sun, who once upon a time grazed in the fields of the Venetian Isle of Sicily, divided into 4 herds, different colors, white, black, yellow, dapple, etc. in each herd, bulls, mighty number of color. The idea is that it's this extremely long and convoluted set of criteria that give you a ton of different equations and a whole bunch of different unknowns, and you have to try to figure out what each of those unknowns are. So it's kind of complicated, but in any sense, if you spend a significant amount of time to decipher this thing, you can see that for, let's use w for the white, it would have to be equal to half plus 1/3 of the black plus, we'll use y, right? Just using different variables for each of the different colors, and the white bulls and the black and yellow, and etc., etc. And cows, it's just, yeah, I'm just using letters to fill in for all of it. The upshot here is that you get 7 different equations. So 1/4 plus 1/5 d plus y. You get d equals 1/6 plus 1/7 w plus y. I use lowercase w. 1/3 plus 1/4 times b plus b, and lowercase b. 1/4 plus 1/5 D plus D. What I mean is, so we have white bulls, black bulls, dappled bulls, yellow bulls, but then we have the exact same colors for the cows, so white cows, black cows, dappled cows. Let's keep going. So D equals 1/5 plus 1/6, y plus y, and then the yellow cows 1/6 plus 1/7, white bulls plus white cows. Okay, so we have 7 equations. We're missing an equation for the yellow bulls, but that's fine. It ends up giving us a matrix. So let's see if I can write it out. It's quite elaborate. We have 6 minus 5 minus 6, 0, 0, 0, 0, 0, 0, 20, minus 20, minus 9, 0, 0, 0, 0, minus 13, 0, minus 42, 42, 0, 0, 0, 0, 0, minus 7, 0, 0, 12, minus 7, 0, 0, 0, 0, 0, minus 9, 0, 20, 0, minus 9, 0, 0, minus 11, 0, 0, 0, minus 11, 30, and minus 13, 0, 0, 0, minus 13, 0, 42, 0. Okay, so that's our giant matrix. I plugged it into a calculator to get that there are 10,366,482 K white bulls, where K is some parameter because this matrix actually has infinite solutions. B is 7,460,514 K. Y is 4,149,387 K. D is 7,358,060 K. W, or little w for the cows, is 7,206,360 K. And then the black cows, 4,893,246 K. And then 5,439,213 K for the yellow cows, and last but not least the dappled ones at 3,515,820 K. So I guess the smallest values you get would be for K equals to 1, but you can plug in whatever K you want. The Bakshali manuscript is an ancient work of Indian Hindu mathematics dating from around the 4th century AD, although some of its materials undoubtedly come from many centuries before. It consists of about 70 leaves or sheets of birch bark containing mathematical problems and their solutions. Many of its problems are so-called equalization problems that lead to systems of linear equations. One such problem on the fragment shown is the following. One merchant has 7 Asava horses, a second has 9 Haya horses, and a third has 10 camels. They are equally well off in the value of their animals if each gives 2 animals, one to each of the others. Find the price of each animal and the total value of the animals possessed by each merchant. So this gives us, again, a system of equations, first of which is 5x plus y plus z equals k for some k, then x plus 7y plus z equals k, and then x plus y plus 8z equals k. And we can come up with a solution to this by following what the manuscript said to do, which is to take 4x and set it equal to k minus x plus y plus z, and take 6y and set it equal to k minus x plus y plus z, and lastly use the last equation to get 7z equals k minus x plus y plus z. That way each one is set equal to k minus x plus y plus z. So we have that 4x equals 6y equals 7z equals k minus x plus y plus z. So what we can do is take the numbers 4, 6, and 7, since 4x plus 6y equals 7z all equal k minus x plus y plus z. That means that this is divisible by 4, 6, and 7. So that means that 4 times 6 times 7 has to equal 168, and that must be divisible by this, so we could just set that equal to k minus x plus y plus z to get a solution. And we do that, that gives us x equals 42, y equals 28, and z equals 24, where k would be 262. And obviously that's not the only solution to this problem, but that's how the manuscript said to solve it.